go.
So Jeff is a collaborator, friend, colleague. He got his PhD in mechanical engineering at USC. He was working with Paul Newton on game theory and treatment optimization of different kinds of competitive release. He's now been at Moffitt working with Sandy Anderson on adaptive therapy and spatial systems and heterogeneity. He puts together the Math Onco newsletter, and he helped organize this conference. So today he's talking about towards multi-drug adaptive therapy.
Awesome, thank you, Jill. Can you see my slides okay?
Yep.
Sweet. Okay, so I have the fortunate pleasure of presenting last. So what I'm going to try to do is think more conceptually today and less on the model details, especially since some of the models that I'm presenting have already been presented previously. And so I'm going to sort of talk about 4 different papers, and not all 4 of these papers are specifically about multi-drug adaptive therapy, but I'm going to pull out the multi-drug component of each of those papers, which might just be 1 figure or several figures. And these papers are roughly organized into clinically feasible approaches of multi-drug adaptive therapy that we could implement today, and more conceptual ideas for tomorrow with the requirement of future technologies, especially for measurement techniques. So to get our brains warmed up, I'm going to think about this using a Mueller plot where we have 2 different drugs, purple and orange drug. And when the purple drug is given, we have the relapse of resistance, and we give our second-line therapy in orange here, and we get the relapse of resistance to the second therapy. The goal of adaptive therapy is to space out treatment holidays to maintain a stable tumor volume in blue of the sensitive cells suppressing these resistant cells. But the story becomes more complicated when we consider how to give those 2 drugs adaptively as opposed to just giving 1 drug adaptively. Should we give the purple adaptive course and then switch to the orange? If so, when should we switch? Or maybe we should stack them together and then just do adaptive therapy like normal, pretending that these 2 drugs are just 1 single agent. In order to think about what the purpose of adding a second drug is, I'm going to talk about the first paper, which is Maxi Strobel's recent cancer research paper that was released about a month ago. He mentioned this briefly in his talk. It's a Locke-Volterra competition model with a Norton-Simon drug effect. And the summary schematic of the model is over here. Basically, we found that turnover helps aid the competition between sensitive and resistant cells. And as such, there's a couple different strategies we could implement by adding a second drug to increase the benefit of the adaptively administered first drug. So the first strategy is reduce the resource supply. We think of this as decreasing the carrying capacity shared between sensitive and resistant cells. And the second strategy would be increased turnover, which increases the death rate of both sensitive and resistant cells. So this is probably the most simple approach. Is if you have a resource reduction drug or a turnover increasing drug, you just give them continuously and you administer your first drug adaptively. And so could we do a little bit better than that and administer these 2 drugs in a smarter way? That's the second paper I just want to mention, where again, Maxi Strobel has implemented an agent-based extension of that Locke-Volterra model, and he tries out 2 different secondary drugs here again. The first is a pro-turnover treatment, but only administered during the off-treatment period of that regular adaptive therapy. So what's the idea of this treatment? It's turnover increases competition, So can we increase competition during the off-treatment periods while the sensitive is regrowing, helping the sensitive to regrow in a more robust way? The answer to that is yes. So the vertical axis here is the relative effect on either sensitive or resistant cells. So if we have a turnover treatment, if we're targeting more strongly the resistant cells and not targeting sensitive cells at all, that's the bottom row here. And then left to right is the increased rate of turnover. So you can see that increasing the turnover, especially when it's targeted to resistant cells, has the highest gain of time to progression for adaptive therapy. The second idea in that paper is pro-proliferation on the off-treatment periods. So this might sound counterintuitive at first glance, but what we want to do is kill the tumor adaptively, and then on the off treatments, try to give a pro-proliferation treatment. And the idea here is to increase the protective shell of sensitive cells around those red resistant cells here in order to increase the competition of resistant cells. So if sensitive cells are already outcompeting resistant, what if we just give a proliferative drug off treatment in order to increase that shell of competition? And this idea doesn't work as well as the previous idea, where the optimal is just to leave well enough alone and not give this pro-proliferation treatment between off treatment cycles. Okay, so that gets our brains warmed up thinking about what is the purpose of giving that secondary treatment. We have a lot of different options to consider, and one option that I'm going to present more in a more deep dive fashion is called a primary secondary adaptive therapy approach. I just like this quote. I think it's a funny quote. Hopefully this isn't true in adaptive therapy, but that's just to keep your attention in between with slides of cool quotes. Okay, so the primary secondary therapy approach, what we did is we published a paper that was an extension of the Zhang et al. Model, which has been talked about previously, where we have producers, dependent and independent cells. And the idea is that these independent cells are resistant to abiraterone because the abiraterone only suppresses the TP and T plus cells. So what we're going to do is add a secondary drug, docetaxel, which targets all of these in proportion to their growth rates. So this is a chemo targeting proliferating cells. We want to consider resistance to docetaxel as well, but so each of these three populations could have a resistant compartment to docetaxel, but we're ignoring the resistance to docetaxel in these two compartments just because we can target those with abiraterone later. So we're only considering the doubly resistant phenotype, which is resistant both to abiraterone and docetaxel. So the idea with the primary secondary approach is that we want to use the primary drug as the drug with the greatest efficacy or the lowest toxicity, and the secondary drug just targets the resistant population that is resistant to the primary drug, which in this case would be the yellow independent cells. So we've seen this before. If you give this model if you run this model without treatment, you get coexistence of producers independent. With continuous abiraterone in blue here, you get the release of independent cells. And if we give it adaptively, we get an extension of the time to progression, but these yellow resistant cells are ultimately the mode of failure here. So what about giving that secondary drug? If we give the secondary drug at the same time as the blue abiraterone, then we get an increase in that time to progression as well. And this time the purple doubly resistant cell type is the one that emerges as the main problem. But you might ask, like, when should we give that secondary docetaxel? And what we did is we looked at every single timing to give docetaxel in comparison to when we give the adaptive administration of abiraterone. So, for example, if we give abiraterone, that's our delta T is 0, if we give them both at the same time, we could shift it to the right, giving docetaxel a little bit after, shift it to the left, giving docetaxel a little bit earlier. And when we look at the percent resistance after one cycle, the optimal time period to give docetaxel is slightly after giving abiraterone. Now, why is that? This delayed docetaxel basically waits until the resistant cell type is maximally proliferating. So you can see if we were to give it slightly before abiraterone, all 3 cell types have a positive slope. Docetaxel targets positive growth rate cell types, and meaning our docetaxel dose wouldn't have as great of an effect because it's targeting all 3 cell types indiscriminately. But here, after giving the dose of abiraterone, these 2 sensitive cell types start decreasing, meaning that any proliferating cells are going to be, by definition, resistant to the treatment because they're proliferating under treatment. So that second drug should be given right when we get the maximum bang for our buck in targeting that resistant proliferating fraction. Okay, so now I'm going to shift gears to the 4th concept, this is from the 4th paper. And this concept is called evolutionary cycles. Now, as I said at the beginning, this is more conceptual and less clinically viable, at least right now. But it would be interesting to think about how we could measure some of these things in the clinic and implement this situation. So what we did is we basically took that population dynamics model, which is Lochta-Volterra style, and then we translated that into a frequency dynamics model where the collapse in the carrying capacity due to treatment is essentially modeled by using a weighting term, weighting the fitness of each cell type. So why do we do this? Well, the key assumption behind an adaptive therapy is that we want to maintain a stable tumor volume. We've heard much about that this week. If we can maintain a stable volume, then we can just shift our attention to the frequency domain, meaning what is the fraction of each cell type at every given point in time. This comes with a lot of caveats, of course. We need to be able to control the volume, and of course, maybe in some situations that might not be possible. But let's just see if we can sort of ignore the complexity of a changing volume and see what the goal would be if we were just looking at frequency dependent domain. Okay, so we're tracking the proportion of each clone over time, and what our goal in driving into an evolutionary cycle is to stack some sequence of treatments such that if we were to take a biopsy at one point in time, the treatment succession later leads to the tumor composition approximately matching your initial starting tumor composition. The implicit idea here is that if you can match your tumor composition, you can repeat these cycles over and over. So what defines a treatment here? Well, if we have N drugs that are possibly administered to a particular type of cancer, then we should have 2 to the n possible combinations, subject to toxicity concerns, obviously, including no treatment as one of those combinations. And we're controlling M cellular phenotypes given by our state vector X, and we want to have a sequence of treatments which changes our X vector such that our X at some time, capital T, is approximately equal to our initial starting composition vector. And to do that, we're going to draw some inspiration from orbital mechanics. So let's say we have a rocket ship orbiting the Earth, and we have some current orbit But what we actually want to do is enter a desired orbit, which is further out from the Earth. This has been well studied in orbital mechanics, and one of the optimal ways of doing this is called a Hohmann transfer orbit, where there is a connecting trajectory which is tangent to your current orbit, tangent to your final desired orbit, and intersects both. And so the rocket ship can land directly on that desired orbit with the minimal energy used. So what is that analogous to in cancer evolution? If we have our phenotype space here on some phenotype axis, and we have our current evolutionary orbit due to some treatment, or maybe due to no treatment at all, what we want to do is look forward in tracing the trajectory, and then look at our desired orbit and transfer to the next desired orbit at the right time. Okay, so what is our phenotype axis that we're considering here? We're going to go back to the Zhang et al. Model and look at producers, dependent and independent cells, this time on a triangular simplex, where every point on the simplex represents a pie chart of some proportion of those three cell types. Again, we're just looking at the frequency, the fraction of each of those cell types, so they should all sum to 1. And here, what we find is if we use this model to plot the trajectories of each treatment, then what we can find the fixed points for each treatment, and Lupron and abiraterone, the standard of care in the prostate cancer trial, has this fixed point at the T- resistant population. And so what we want to do is see, is it possible to drive it into an evolutionary cycle based on this particular patient's parameterization? And it is, and what it looks like is, say if you start at this purple dot, you would eventually go to the fixed point of the purple treatment, which happens to be no treatment. But if you switch to Lupron and abiraterone before reaching the fixed point, then you would go to that fixed point, but then you switch again to Lupron only, and then you reach back towards your initial starting condition. So you can repeat cycles over and over and over. And then you can also see, if we plot the trajectories over top of each other, there's many such cycles that exist. If you go down this blue line, you can pick one of these purple lines to go up, and then down the red line, and then back down the blue line again. So there's a few tiny cycles, a few large cycles. And so next we can think about which of those cycles are optimal in certain scenarios. But it does seem to be possible, at least with this model. Okay, so the last thing I'm going to sort of look into is called evolutionary search space. And that is basically taking those same treatments, but this time 2 by 2. So if we take no treatment and Lupron and switch back and forth between those two, what we're essentially doing is drifting closer to the blue fixed point, then we switch to the purple treatment, drifting closer to the purple fixed point, drifting back to the blue fixed point, and back and forth. And what we get is this absorbing state where all possible combinations of those two treatments tend towards that absorbing area. And what I'm doing is calling this evolutionary search space, because if you treat with those two combinations, you're eventually limiting the part of the domain which is reachable by those two combinations of treatments. And the same happens with each of the other two treatments. This one happens to be a larger search space, so we're limiting ourselves less in these two treatment combinations. And the last one is a very narrow and skinny absorbing state space. Okay, so I think I'm getting short on time, so I'm going to sort of finish up with this and just say that if we add all three treatments in combination, then we can actually expand our state space, absorbing state space region. which makes sense. So the idea would be some sort of orthogonal drug is desirable. If you added another treatment, and that treatment obviously has the same fixed point as another treatment, then it's not going to do any good at increasing your absorbing state space, which also increases the opportunity for more evolutionary cycles. Okay, so I'm going to skip this slide, but this basically says that this is robust according to many different parameterizations. And then this slide shows that the frequency-dependent dynamics are heavily dependent on the velocity at each given tumor composition. And we can also look at the null lines for each of the controlling populations. So for example, the T- population is the one that we want to control. So we should look at the isocline, which determines when that population is growing versus decaying. If you like these plots, you can play around with this tool that we just built called Isomatrix. You can download this on the Math Onco GitHub, and they're really easy to play with evolutionary games, matrix games. Just with one command, you can get the velocities, the isoclines, and the separatrices and basins of attraction, if you're interested in that, and many more other options to play with as well. Okay, so with that, I'm happy to take questions, and I'd like to acknowledge the collaborators on many of these papers, as well as pointing out our cancer research cover image, which is the evolutionary cycles idea, going around and around with the different treatments and trying to aim back at your original tumor composition. Thank you.
Thanks, Jeff. And I'm glad you mentioned Isomatrix. It produces really cool figures there. We have one question here. Indra asks, are doubly resistant cells thought to be burdened with a double compounded cost of resistance? If so, could it be good to speed up a compounded resistance, amplifying the cost of resistance such that adaptive therapy works better?
That's a good question. So in the model, the way we modeled it, the answer is no, we didn't consider a double cost of resistance, but we could. The one driving assumption in that paper was that the doubly resistant cell type is exceedingly rare. So the single resistance is rare, but the double resistance is even more rare. So it's assumed to emerge after single resistance, basically. But I like the idea.
Mm-hmm. I wondered too, I guess if you make it go down enough, it maybe even continuous therapy would do better.
Right,
I don't know.
That is true.
Here's, Carlo Maley has a response to that. We do assume that the doubly resistant cells have lower fitness than single resistance in our agent-based models.
Yeah, I think that is a reasonable assumption for sure.
Mm-hmm. Okay, there's another one here, anonymous. Why do you consider frequency dependence but not density dependence? Is it clear that there is no density dependence? Population size changes should be observed during treatment such that densities matter.
Yeah, I totally agree. Yeah, this is something I'm very interested in. This is why I asked the question during Artem's talk about density dependence and how to measure this. And so the way I think about it, at least from the modeling perspective, is we've been using these evolutionary game theory frequency dependent models just as a way to see, what is important in the frequency domain. But then the first few papers that I presented are looking at density dependence specifically in the locked Volterra models. So I agree that they're both important, but so far we've sort of taken them one at a time, and it would be good to look at them both in the future together.
I have kind of a broad question, maybe to do with just having multiple drugs in this adaptive therapy type of strategy and what you might think about it. And in your examples here, you have one of the drugs is actually no drug. But when you start to think about this, is there a certain point, I know some models consider toxicity, but once you start just kind of putting it into this loop and continuously having drug, have you considered how that might affect? I mean, because I know a lot of times it's the volume that's minimized, but it's also toxicity.
Yeah, that's a good point. Yeah, so I think one of my first interests in the idea was just to see if it was possible. Is there an evolutionary cycle in the system? Like, is it possible? And the interesting thing is that it is possible, and there's many different evolutionary cycles that do exist. So the second step would be choosing which evolutionary cycle is the best, right? So maybe some of these evolutionary cycles slowly increase the tumor volume over time, or maybe some of them have a higher toxicity, things like that. So we can sort of go back to the density dependent domain, or go back to toxicity concerns, and choose which of those cycles is going to be optimal. So yeah, I love that question for sure.
Well, and maybe to follow on that, stuff that I hadn't seen before was that kind of velocity dependence through the space, and maybe that could be changed by dose. And
right, yeah, that's a great point, because this is just looking at a single dose, like the max dose with treatment holidays, but with dose modulation, this gets even more complicated.
well, thank you very much.
Yeah, thank you.